Hello everyone, welcome back to part 2 of chapter 9. In the first video, we discussed how we could take a system of particles and combine not only the position of those particles, but also the contribution that each of those particles makes to the entire system in terms of the percentage of total mass that was in that system. And from that, we were able to construct this expression that tells us how we can find the center of mass for a given system. So what we have here are two summations. The summation in the top half of our quotient here is the sum of the products of each individual mass times its individual location on the x-axis. And in the bottom, what we really have is just the total mass of the system produced by the summation of all the mass in the system. And what this does is it tells us how each mass contributes to the overall center of mass for the system. And then we can take that system of particles and we can replace it with one equivalent mass that will do the same job. And we could reproduce this expression for the y-axis, the z-axis. We could also plug in some time dependencies, turn these into displacements, velocities, accelerations, etc. So that was everything that we had in that last video. But now we want to take this a step further and see if there's a way that we can find the center of mass for solid objects. And these solid objects have millions, if not billions, of individual particles, and we don't have the time to sit around adding up all of their contributions. We did mention in the previous video that we could put something like this equation into our computer, like an Excel program or another type of simulation software, but that's going to take time to set up. It's going to take time to input the data. It's also going to take time for the computer to process that data. So instead, we want to see if we can maybe cut some corners in terms of how we're going to do this math. So let's take a brick of material, and it's always kind of challenging to draw 3D on a 2D surface, so I'm going to do my best here. Might have to use our imagination a little bit. This actually isn't looking too bad. Alright, so we have our brick of material, and we'll say that this brick has a length of L, a width of W, and a height of H. And we're going to assume that there is a uniform density for this material. So whatever it is, it could be some kind of ceramic, glass, metal, styrofoam, you name it. We just want the density to be uniform. And what that means is that for any given amount of mass per unit volume, that ratio has to remain constant throughout the entire material. And that means that the ratio of the total mass to the total volume will have to equal the same ratio of any sample that we take. So if I were to cut this corner piece off here, the mass of that corner piece and the volume of that corner piece, the ratio of all of that would have to equal the same ratio as what the total ratio equals. So we'll backtrack this a little bit. All right. And it's the uniform density idea which is actually going to make our life so much easier. And that's because with uniform density, and if our object has any kind of symmetry that we can take advantage of, and in this case, it's a very symmetric object, we can bypass a lot of the summation stuff just by using some common knowledge, which is if I were to cut this brick in half along its length, so each half has a value of L over 2. Each half has the same volume of L over 2 times width times height. And because each half has the same volume with a uniform density, then each half would have to have the same amount of mass. And this is critical to our idea because, I'm going to redraw that because it didn't quite look right. There we go. This is critical because we can now say that on either side of that cut that we just made, we have the same amount of mass on either side. And that means that the center of mass for this brick has to lie somewhere. I'm going to try drawing this cut three-dimensional if I can. So that means that the center of mass has to lie somewhere on that cut that we just made. But the problem with that is that that cut represents a two-dimensional plane, and there are still far too many points on that plane, whereas we just want one single point that will act as the center of mass. And that one single point in space is going to have values of x, y, and z that represent the location of that center of mass. Well, right now I've only got one of those values. It's L over 2. And if we need to, we could define a reference frame. I'm going to use the back left corner here as our reference frame. And we'll say that this is the z-axis. We'll say that this is the x-axis, and then the y-axis can run back this way along the width of the brick. So I guess that means we should have like a three-dimensional representation. So now this brick is translucent, and we can see through it. But this means that we now have the x component of our center of mass, because that center cut lies on the x-axis and it was made at a value of L over 2. Well, we can reproduce this quite easily along the other dimensions of the brick. If I cut the brick in half along the y-axis, again, it's been cut in half, and so the amount of mass that is in front of that cut will have to equal the amount of mass behind that cut, and that means that the center of mass for the system will have to lie on that plane as well. But now we're actually narrowing down the possible points that can be allowed, because if our center of mass has to lie on both of those planes, well, the only location where both of those planes exist together is at the intersection between those two planes. So now I have a line where my center of mass has to exist, and this other half cut that we just made there was half the width, and so that means that the y component will have to be at half the width. And as you can probably imagine, the last piece of information that we need is for the height, and we can cut this mass in half along the height, just as we did along the length and the width. And this is getting kind of messy here, but when we take all three of these cuts, there's only one point in the entire object where they all intersect. And let's see what color. I'll use this bright blue. And that's going to be right at the geometric center. And we can say that because we're using a uniform density, and this is a very symmetric shape. So we have our half cuts that tell us that the center of mass for the entire brick has to be at the half values of x, y, and z axes, and now we know the center of mass for that object. Very straightforward idea, very easy to do. Really all we have to do is just cut the object in half, and as long as we have the same amount of mass on either side of that cut, then we can make the assumption that the center of mass has to be on that cut. We reproduce those cuts through the other axes, and we find our center of mass. Now, if that's all it takes, well, what happens if we have a mass that's not so symmetric? What if we have a mass that looks something like this? So let's say we have a piece of sheet metal, and someone's already been here, they've cut some pieces off of the sheet metal, and so the original dimensions of that sheet metal would have been length times width times this sheet metal will have some kind of a thickness to it, but that thickness should be uniform. Right now it's the length and width cuts that we're really concerned with. So length, width, height. So we'll just say the height is synonymous with the thickness of the sheet metal. And since the thickness of the sheet metal is uniform, what we can do is we can just assign that a value of 1. And then we'll worry about the length-width combination, because that's really what's going to tell us where the center of mass for this particular piece of sheet metal needs to be located. I'll put a reference frame at this bottom corner. So we do have to have a reference frame for these kinds of problems so that we can measure physically where things are located. But I'll put everything in the first quadrant of our XY reference frame so that everything is positive. Now, if I had the complete unaltered piece of sheet metal, the center of mass for this system should just be at half length, half width. So whatever this length is, we'll call it L. Whatever the width is, we'll call it W. And so the halfway values for these would say that the center of mass should be right about there. But we've lost a good portion of the mass in this top right corner. That means that we should see our center of mass shift further towards the side that has mass. we're going to find where this new center of mass is located. Now, to do that, we need a little more information about this system. Let's see here. Clean this up a little bit. We'll say that this thing is 8 units long. So maybe we could say feet. So this is 8 feet long, and we'll do 2, 3, 4, and 6 feet high. So an 8 by 6 piece of sheet metal. It's been cut, and now what we need to do is we need to get measures of every side of the remaining sheet metal. Now, we already know that this far left-hand side has a value of 6. We know that the bottom side has a value of 8, but now we're going to go around and measure the dimensions of all the remaining sides. This portion right here, if we look down on the x-axis, takes up a value of 2. This value right here takes up a value of 1, 2, 3. And this portion right here takes up a value of 1, 2, 3. And we do need to make sure that whatever the total length is up here, that it matches the total length down here. And it does after I get the right numbers in. There we go. 2 plus 3 plus 3 makes 8. And we're going to do the same thing on the y-axis. For the y-axis, I have this piece right here, which is taking up a length of 2. We have another piece that is taking up a length of 2, and then the final piece, all that's left is another 2. Oops. Switch back to the pencil. There we go. All right, so all sides of our mass have now been measured, and I need to know what these measures are, because with a uniform density, we're going to make this assumption about the sheet metal. It should be of uniform density. Otherwise, if it's not, then it's not a very good quality sheet metal. But with that uniform density, we can take advantage of this mass and volume relationship. Now, we can find the volume of this sheet metal. Like we said up top, the dimensions are length, width, and thickness, which we said we were just going to give a value of 1. And that way we don't have to worry about the thickness. But this is the volume of what piece, or how much. And things worked really well for this brick because the brick was symmetric. Is there a way that we could take this asymmetric piece of sheet metal and turn it into something that's more symmetric? And we can do that if we segment the sheet metal. What do I mean by segment it? Well, we're going to divide the sheet metal into sections that are symmetric. And if we look at this sheet metal, how many different symmetric pieces can you make? And the answer is a lot. You could cut this thing up into as many pieces as you want, but we want to find the minimum amount. And what I can see from this picture, the minimum amount of sections that we can make is 3. And I'll give you a couple of examples. We could take this section. That 2x2 section is a symmetric section of the sheet metal. We could then take this section as a symmetric piece of the sheet metal, and then that leaves us with the third section here. And those are 3 separate symmetric shapes. Each one of those shapes, I can apply that half cut approach that we did up here with the brick. And if I can find the center of mass for each of these sections, for instance, there should be a center mass right there, there should be a center mass right here, and there should be a center mass right here. Well, I could take these 3 individual sections and I could turn this into a system of equivalent masses. And the equivalent mass at each of these sections could then be used in a summation expression. And that summation expression can tell me where the center of mass for the entire construct is located. Now maybe those are not the sections that you were thinking of. Oops, get my eraser going there. Are those the only 3 sections that you can use? And the answer is, of course not. I could make this section, and I could make this section, and I could make this section. So 3 very different segments of the same object. But regardless of how I segment this sheet metal, all of the material is still there. All of the material is still distributed about the same total volume. I'm still going to get the same center of mass for this system, regardless of how I segment. The only thing that we have to do now is we have to decide, how many segments do we want to be working with. And the more segments that you put in here, the more work that you're going to have to do. We can always segment this thing more, but now I have a system of 6 point charges, essentially. I'm taking each segment and I'm going to convert it into a point charge equivalent, but it would be a lot easier if I just had, say, 3 segments to work with. Because then I just have 3 things that I have to plug into my summation equation. So that's what I'm going to do. I'm always on the lookout for doing the least amount of math possible, because that is going to reduce the possibility of me making a mistake with my math. So these are the 3 segments that I'm going to use, and I'm going to call this segment M1, this will be M2, and this will be M3. Now, why am I calling them M1, M2, M3? Well, that's because each of those segments will have a mass that is associated with it. And I need to know how much mass each of those segments has. We will use the uniform density expression to help us with that. Regardless of the mass that we're talking about, the ratio of each mass to its volume must equal the same density. So M1, M2, M3, we can compare those to the volumes that they are taking up. And this is why we took the time to figure out what the dimensions of all the different sides were. If we look at mass 1 has dimensions 2 by 2. Right there, 2 by 2. So 2 times 2 is 4, 2 times 2 is 4, times the default thickness of 1. I'm still getting a volume of 4 for mass 1. And that means that mass 1 can now be represented as the uniform density times the volume. And since mass 1 has a volume of 4, I can now say that mass 1 has a value of 4 rho. I don't know what the density of this sheet metal is, but we'll just go with it. We've already run into plenty of problems in this course where it looks like we might need some information, but then later on it factors out or cancels. So we'll see what happens along the way here. For mass 2 will have to equal the uniform density times its volume. Let's come back to mass 2. What are the dimensions of mass 2? Well, mass 2 has a width of 1, 2, 3, 4, 5, and a height of 1, 2, 3, 4. 4 by 5 is 20 with a uniform thickness of 1. So we have 20 rows for mass 2. Sorry. Mass 3 is going to be uniform density times volume 3. Mass 3 has dimensions 3 by 2, which is 6. So 6 row. What do I do with all those? Well, we can find the total mass of the sheet metal right now. All we have to do is add up all the individual masses that we have. 4 and 20 and 6 makes 30 rho. And that's a really good portion of everything that we need to go into this equation. The only thing that's left is that I need to know where each of those masses has its x value. So we'll come back down to the picture here. And now is where we get to play the bisector game. We're going to come in and bisect each of these masses. We already know that they're uniform in density. The whole purpose of selecting symmetric segments was so that we could actually bisect them. And now I need to know what is the ordered pair that describes the center of mass for mass 1. Well, mass 1 has an x component of 1 and a y component of 1, 2, 3, 4, 5. So mass 1 has 1, 5 for the ordered pair, describing its location, or its center of mass location. For mass 2, is 5 units long. Oops, had my eraser on. 5 units long, so half of 5 is 2.5. It was 4 units high. Half of 4 is 2. So there's the ordered pair that describes the center of mass for mass 2. It's at 2.5, 2. And then mass 3 Mass 3 was 3 units long, 2 units high. Half of 3 is 1.5, half of 2 is 1, but got to be careful now. I don't want to put in 1.5 and 1 because that's incorrect. It's true the center of mass for mass 3 is located at the half point, but where is that half point when measured from our reference frame? Because the other 2 points, mass 1 and mass 2, were measured from the reference frame, but they were actually stacked up right against that reference frame. So we need to take the length of mass 2, which was 5, and add that to the 1.5, so that's 6.5. 6.5. The 1 is okay because we're still just 1 unit above on the y-axis. We now have everything that we need to carry out this summation process. And it's not just going to be for the x-axis, we're also going to do this for the y-axis because this is a 2-dimensional shape. So we're going to find the x component of the center of mass, and then we'll come back and we'll find the y component of the center of mass. All we have to do is switch out the x's for the y's in our equation. But we still don't have the rho value. Well, that's okay. We can always continue on with a general solution, and we'll go as far as we can go until we actually need some numbers. But in carrying out the summation, we have the sum of each individual mass times its individual x value. So we need mass 1 x1 plus mass 2 x2 plus mass 3 x3 all over the total mass of the system. Mass 1 has a value of 4 rhos. Its x value is 1. I'm just pulling information from right up here. Plus mass 2 has a value of 20 rho. It has an x value of 2.5. Plus mass 3, 6 rhos. It has an x value of 6.5. And that will have to be divided by the total mass of the system, which is 30 rhos. Well, now you can see that everything is going to be okay because every term on the top has a rho, our bottom term has a rho, all those rhos are going to cancel out, and we're only left with numerical values. So we'll put these into our calculator. We have 4 times 1, which is 4, plus 20 times 2.5, plus 6 times 6.5. That gives us 93 all over 30 equals 3.1. Now all of the dimensions that we had for this piece of sheet metal, we said that we were using feet. Well, so now we know that the x component of our center of mass is at a value equal to 3.1 feet. For the y component of the center of mass, we need mass 1, y1, mass 2, y2, mass 3, y3 all over the total mass. Mass 1 is 4 rows. Y1 was 5. Mass 2 is 20 rows. Y2 is 2. Mass 3 is 6 rows. Y3 was 1. All over 30 rows. Again, all the rows cancel out. We end up with 20 plus 40 plus 6. 66 over 30 equals 2.2. So there is the center of mass for this piece of sheet metal that has been cut up. And I'm going to go through and get rid of all these crosscuts and whatnot, just so we can see things a little bit better. Because remember, we said that the original piece of sheet metal had dimensions of 6 by 8. And if we had all of the sheet metal there, if it had not been cut up, then the center of mass should have been at the center, which would have been 4 by 3. But now, because a lot of the sheet metal has been removed, that center of mass has been relocated to a position of 3.1, 2.2, which is right about there. So we've seen our center of mass shift accordingly by removing that mass. All right, so now that we've seen this example, it's actually a pretty straightforward idea in taking an asymmetric shape and breaking it down into something that is symmetric, so that we can use the point expression for finding the center of mass of the entire thing. But again, the whole idea is to break the system up into as few pieces as possible. So if we had a piece of sheet metal that looked like this, what would be the minimum amount of cuts or segments that you could break this object up into, so that you could apply this point charge idea? And remember, the fewer sections that you have, the better. And right now, it kind of looks like we could just segment this into a whole bunch of different pieces. But again, that's way too many. That's way too much work. If I were doing this problem, let's see, I could get away with 4 individual segments. That's the smallest amount that I can see, and I would do that by segmenting those 3 parts. So I would have a center of mass for the first part, a center of mass for the second part, a center of mass for the third part, and then all this other stuff here, well, that's a symmetric rectangle, which would have its center of mass at its center. I don't need to break that up into a bunch of smaller pieces. If that's not the arrangement that you were envisioning, that's fine. You can use a different arrangement. Maybe this. That's also 4 pieces. Each segment would have its own center of mass, and we would treat those as a system of particles, and we would find the center of mass for the object. regardless of how you break up the object, it still has to have the same overall center of mass. So it might even be a good side exercise to take what we had up here and maybe try breaking up this piece of sheet metal into different segments instead of what I had labeled. I had these 3 segments. Maybe try those 3 segments on your own and make sure that you can reproduce the same center of mass values. So that brings us to the end of part 2. And this also brings us to the end of the center of mass portion of the chapter. When we come back, we're going to start talking about momentum. But the idea of center of mass is really important because when we get to the next chapter of chapter 10, we're going to start talking about objects that are rotating. And an object will rotate about its center of mass. And not every object that's out there is the same shape. Not every object that's out there has the same center of mass. But every object will rotate about its center of mass. So if I had a block and I started rotating it, well, this point, that center of mass, will remain fixed, but all other particles will have to rotate around it. If you've ever seen somebody toss a baseball bat, that baseball bat is thicker on one end than another. In terms of the length of that baseball bat, well, the center of the baseball bat would be right there. But the baseball bat has a lot more mass towards this end. As such, the center of mass of the baseball bat is going to be much further out. And so if you've ever seen somebody toss the baseball bat a little too much, you're not supposed to throw the baseball bat when you're playing baseball, but you'll see that baseball will kind of tumble end over end, not at the center point, but somewhere within the thicker portion of that bat. And so we're going to combine these ideas of center of mass from chapter 9 to the idea of a rotating body in chapter 10. But we need to talk about momentum first, and so that'll be the next 2 videos of chapter 9, and we'll see you at part 3.